Welcome everybody to section 10.6 of geometry, area of regular polygons. So first we need to recap what is a regular polygon. A regular polygon must be three things. First, it must be convex, meaning that all the sides point out, none of them cave in. It is equilateral, meaning all the sides are congruent. And lastly, that it's equiangular. So all the angles are also congruent. So those three things, it is a regular polygon. So let's do the area of a regular polygon. It'll be capital A is equal to A times S times N all over 2. Didn't really get on my line well. So we need to know what A, S, and N are. A is the apothem, which we'll learn more about in just a moment. S is the side length. I should really fix that M on apothem there. And N is the number of sides. So the apothem is going to be the perpendicular segment, meaning it makes a right angle, from the side of a polygon to the center of the polygon. So we can see here in this pentagon that we have this segment going from the center of it to where it's going to the side, and it makes a right angle, meaning that is the apothem. On this first example, we're going to have this octagon, RSTUVWXY. And it's a regular polygon, meaning all the sides are going to be the same, all the angles are the same, and then that is also convex. And it's inscribed in circle C, which means that every vertex is on circle C, even though some kind of look like they're off. Since we're told it's inscribed, it is inscribed. And we're supposed to find the measure of angle RCY right here, measure of angle RCV, and the measure of angle ZYC. So to first find the measure of angle RCY, we're saying, okay, well this is going to be part of this triangle. Well, it's also part of a circle. And so this would actually be a central angle in the circle since the vertex is at the center C. Well, we know a full circle is 360 degrees. But we just want part of it. So we got to figure out, well, how much of it do we want? Well, if we realize that, hey, this central angle also takes up one side of this octagon, we can make another one here that takes up another side, and a third, and a fourth, and they all form these triangles. Fifth, sixth, and then with this line I make 7 and 8. So really, if I just take this 360 degrees of the whole circle divided by 8, I'll get each of these angles, which is what we want to find. So we'll take 360 divided by 8, and that gives us 45. That tells us that the measure of angle RCY is 45 degrees. I'm going to go ahead and label that here as well. Next, we need to find the measure of angle RCZ. Angle RCZ. Well, how we can find that is actually knowing that R to C, the segment here, and Y to C are actually both radii because they go from a point on the circle to the center. Now, because this is an isosceles triangle, triangle RCY, when you take an isosceles triangle and you put an altitude in it, meaning a perpendicular segment for the height to the vertex like that, it always bisects this angle, meaning that 45 degrees is cut in half, making angle RCZ 22.5 degrees, or half of 45. So I'm going to label that in here too, like, hey, this tiny little angle is 22.5 degrees. Now, using that information, we want to find angle ZYC. Okay, well, we said if this is 22.5, so is this one. That's going to be good to know. And we know that this is 90. So if we use those two facts, we can find this angle by taking 180 minus 90 and 22.5, or saying, well, these two have to add up to 90, and taking 90 minus that 22.5. So we get the measure of angle ZYC to be 67.5 degrees. And now we found those three angles. I'm wondering, like, well, why does this even help? This doesn't talk about area at all of those things. And those would be great questions. And it's actually because we're going to be utilizing this method of making a triangle out of a shape and then finding the angles inside of that triangle to help us find different measures so we can find the area. It's kind of a lot of so that, so that, so that. I think we'll see it a little bit more here, though, on example 2. So in example 2, we're tiling a floor with ceramic regular hexagons. So each of these is a tile on the floor, and each side length of this hexagon is 8 inches. And it's a regular hexagon, meaning all the side lengths are congruent. And we want to know the area that one specific tile will cover. So we have our one tile pointed out. Well, in order to know that area, we said capital A area is going to be equal to the apothem times the side length times the number of sides. Well, right now we don't know the apothem. We know the side length is 8 inches, and we know the number of sides is 6. So if we do know the apothem, or if we find the apothem, then we can find the area. So, well, we got to figure out the apothem now. We're actually going to utilize that same little trick or same method we did on the last problem where we had it circumscribed in a circle. I should say inscribed in a circle. Circumscribed would be different. Circumscribed would be the circle inside the hexagon rather than the hexagon inside the circle. So we're going to utilize the same exact method and make a triangle from the point. And just like with an octagon on the previous example, we took the 360 degrees that makes up the whole circle and said if we divided by 8, the number of triangles we would make, or central angles we would have, we found the angle. Well, this time we can make 6 since there are 6 sides. Meaning just one of those would be 360 divided by 6, or 60 degrees. So that makes this angle 60 degrees. And it would also make these two sides congruent because they would both be radii, going from a point on the circle to the center of the circle. And that's what this little triangle over here is for us to actually kind of zoom in on this, but just to do it over here so that way we can draw on it well. So we said this big angle is 60 degrees. And we know that these two lengths are both those 8 inches. Just like on the previous problem where we said we can actually draw a right angle going down here, an altitude, and it'll bisect this angle. So that means rather than the whole thing being 60, each of them are 30 degrees. And just like we found in the last example, this angle after that, we'll do it again and say, well, this one is actually going to be 60 degrees. And because this one is 30, this one has to be 60. So that way 30, 60, and 90 can add to 180 degrees for the triangle. Now, 30, 60, 90 might sound familiar to you. Hopefully it does. That was one of our special right triangles back in chapter 7. So special right triangles, we can use this to help us, knowing that this down here would be the short leg, and this here would be the long leg across from the 60 degrees. And this up here is the hypotenuse. Well, to go from hypotenuse to short leg, you divide by 2. So we're going to take the 8 divided by 2 and find that this is 4 inches. And that would make sense that that's 4 inches because the whole thing we said just a bit ago was 8 inches. And well, last I checked, 4 is half of 8. So that makes sense. So now we need to find this here though. That's the whole reason we did it. That would be the height of this triangle, or as we can call it, the long leg being opposite 60 degrees. And it will also be the apothem, because zooming back into this hexagon, let me use a different color here, zooming back into this hexagon, that would be from the side perpendicular to it to the center. So that's what we need to find here. Well, if we recall, in a special right triangle, in order to go from the short leg to the long leg, you multiply by the square root 3, meaning that it would be 4 square root 3, and we just leave it there. So that is our apothem, 4 square root 3 inches. So we plugged it into our formula. Oops, I miswrote on our formula. You might have caught this earlier. I'm sorry I did not catch it earlier, but I'm only catching it now. That it's apothem times the side length times the number of sides divided by 2. So now I'll write this in. Area is equal to the apothem, 4 square root 3, times the side length, 8, times the number of sides, 6, divided by 2. And we can multiply all of those together, and we can type that all into our calculator if we want at once, or you can space it out. Let's say we do space it out, and we do 4 times 8 times 6, so the regular times a regular times a regular number. You get 192 times the square root of 3 over 2 square inches. Now we would still need to divide the 192 and the 2, so let's say we do that next. And we end up with 96 times the square root of 3 inches. Now, that's the exact length because we haven't rounded yet. However, even though that's the exact length, and it is an answer, it's not as practical. If I go into a tile store and I say, okay, I need 96 times the square root of 3, I need a tile that can cover 96 and the square root of 3 square inches. I should have put square inches on that. That's not going to be very helpful to anyone. Or if the tile person tells me, hey, this is how much it'll cover, I'm going to sit there and say, okay, well, what's that close to? Like, what's that approximately? And so then they would say, okay, well, 96 times the square root of 3 ends up being an approximate area of 166.28 square inches. And so that would be an approximate answer, which would be a lot more useful in this scenario. So that was a lot of steps on this problem. To recap, we had our area formula, which I miswrote earlier, but it's apothem times the side length times the number of sides over 2. So we needed the apothem, we had the side length of 8, and we knew the number of sides to be 6. So we started off similar to the previous problem, where we made a triangle out of it, and we said, well, one of these angles is going to be 60 degrees. We cut that angle in half when we made an altitude. It's altitude right here, which made that this angle is 30 degrees, the other angle was 60, and so then we used our 30, 60, 90 triangle to find the apothem to be 4 square root 3. Then we plugged in our numbers and solved from there. One last example today, another long one, a regular decagon. Reminder, a decagon is 10 sides. So we have the decagon right here, and we're told that it's inscribed or in a circle with radius 8 centimeters, meaning that this is 8 centimeters here, and it's also 8 centimeters here. And you notice the problem jumps immediately from the decagon in the circle to having all of these triangles already made for us. That's helpful because then that helps us say, okay, I need to go from 360 and divide by 10, meaning each angle is 36 degrees. So I'm going to write that in here, 36 degrees. If you can't get that in there, drawing an arrow and writing it to it outside is perfectly fine. Now we're supposed to find the perimeter and the area of the decagon. Perimeter won't be too bad because we just need to find the side length and add the side lengths up, or take side length times the number of sides. Area, though, like we talked about, is going to be the apothem times the side length times the number of sides over 2. So we need to know the apothem, which we don't know, a side length, which we actually don't know either this time, and the number of sides, which we know to be 10. So zooming in on this triangle again, we said, hey, each of these side lengths are going to be 8 centimeters, and this big angle is 36 degrees. Well, an isosceles triangle, we're going to draw this altitude in here, and it's going to bisect this angle, meaning each of them are 18 degrees, and to add up to 90 with this other angle 18 degrees, this angle down here has to be 72 degrees. Now, this time we don't know this side, and we don't know this side either, of this right triangle we made out of this triangle. And we can't use a shortcut because it's not a 30, 60, 90 or a 45, 45, 90. Meaning, we actually have to go back to using trig functions, or SOHCAHTOA. How rude of me to bring this stuff back. So, whichever angle we pick, let's say I pick the 72 degrees. You could pick the 18 and it'd work just fine. But let's say I pick the 72 degrees. Well, from the 72 degrees, this side right here is the adjacent side. This side over here is the opposite, and the 8 centimeters is the hypotenuse, and it would have been regardless of which angle we chose. So I need to find the adjacent side, because that's going to be half the side length, and I also need to find the opposite, because that's going to be the apothem. So let's say I start with the adjacent first. I want the adjacent, I have the hypotenuse, so that tells me I use CA. So I'm going to say cosine of my angle, 72 degrees, is equal to the adjacent, I'll call it x, over the hypotenuse, 8. And we solve this by multiplying 8, or 8 over 1 on both sides. We get 8 times cosine of 72 degrees is equal to x. We plug in 8 times cosine of 72 degrees into our calculator, and we get x to be approximately 0.247 centimeters. 0.247, excuse me, I misspoke. 2.47 centimeters. I need to move that decimal. 0.247. Well, that's way too big. Meaning the entire side length, the S, would be double that, or approximately 4.94 centimeters. So I can add that into my S. I know that now, 4.94 centimeters. And now I need to find the apothem. So that'd be the opposite side now. So I want the opposite. I have the hypotenuse. I also have the adjacent, but I don't want to use that since it's not as nice of a number, but more importantly, since it's something we already found and rounded. So we don't want to deal with that. We want to go with 8, which was given and exact. So I'm going to use sine, though, the so. So sine of 72 degrees, the angle, is equal to opposite. I'm going to call this one y over the hypotenuse, 8. Solve this one in a very similar fashion by multiplying by 8 over 1, or 8. I'm going to have 8 times the sine of 72 degrees is equal to y. So I simplify that, and I get y to be approximately 7.61 centimeters. And I don't need to multiply this one by 2 because it's already the entire opposite side, the entire apothem, whereas the adjacent was just half of the side length. So I make that 7.61 my apothem. And now I can plug these in. Area is equal to 7.61 times 4.94 side length times the number of sides, 10, all over 2. And we type that all into our calculator. We let it do the work for us, and we end up getting area is approximately, and we'll go to the nearest hundredth, 2 decimal places, 187.97 square centimeters. We still need to find the perimeter, but this will be a much smaller step because perimeter is the side lengths added up. So you take the 4.94 and you just add it 4 times, or you multiply it by 10 since that's how many sides you have. Meaning the perimeter ends up being 49.4. I really should have an approximate there because 4.94 was rounded. So it ends up being 49.4 regular centimeters because only the area is square units, not perimeter, because you're just adding, not multiplying lengths. So recapping this problem, the reason it was different than example 2 was because it was 18 degrees and 72 degrees, meaning it was not a special right triangle. We could have used trig on this previous example as well, and ended up finding instead of 4 square root of 3, that side length would have been 6.93 rounded to the 100th, because that would be 4 times the square root of 3. And it would be the same thing. All right, that is section 6 today. Finishes up our notes for this chapter. So please refer to Google Classroom or the teacher as far as what your homework will be for the day.